part 2 of the lecture on Copernicus. This is concerned with Copernicus's math. Copernicus's math basically falls into 2 categories. First of all, Copernicus correctly calculates how long it takes each planet to go around the sun. The planet's year, if you will. This is referred to as the sidereal period. He also determines the distance that each planet is from the sun as well. I'll be going through the details of these 2 mathematical steps here in this lecture. However, before we do, we have to begin with a number of definitions. These were definitions that were first coined by Copernicus. We still use them today. Okay, first of all, Copernicus breaks up the planets into 2 categories. We have the planets Mercury and Venus, which are closer to the sun than the Earth is. Copernicus refers to these planets as inferior planets. So that's Mercury and Venus. And then we have the planets that are further from the sun than the Earth, Mars, Jupiter, and Saturn. Copernicus refers to these as superior planets. Mars, Jupiter, and Saturn. Okay, and then for both inferior planets and for superior planets, there are important planetary configurations. Okay, first of all, for superior planets, we have what is referred to as opposition, conjunction, and quadrature. Okay, for the inferior planets, we have what is referred to as superior conjunction, inferior conjunction, and greatest elongation. Okay, now what I want you to do is I want you to pause this lecture and then take a look at the screencast that I've posted for you called Important Planetary Configurations. Watch that screencast now. Okay, so now that you've seen that screencast, I'm going to be referring to a couple of these important planetary configurations as I go through the mathematics of Copernicus's model. The first thing that Copernicus does is it determines how long it takes each planet to go around the sun, what is referred to as the planet's sidereal period. Now this is another definition, so let me go ahead and define that term for us before we go any further. The sidereal period is referred to as P in this description, and it refers to the following. It's the rotation of the planet about the sun with respect to the background stars. The rotation of a planet about the sun with respect to the background stars. This is the planet's true year, if you will. A little bit more strictly speaking, this is the planet's orbital period. However, this is not what we see from our moving platform. Instead, we see another type of period, which is called the synodic period. A planet's synodic period is a rotation of the planet with respect to the sun. The synodic period is referred to as S, and it's a rotation of the planet with respect to the sun. Okay, Okay, as you'll see as I go further in just a few moments, this is what we see from our vantage point on a moving platform on the orbiting Earth. This is what we see from the Earth. Okay, now let me distinguish between the two, and I'm going to use the example of opposition for superior planets in order to illustrate. Okay, so for example, let's say that right here is the orbit of a planet, say Mars, Jupiter, or Saturn. Right here is the orbit of the Earth, and let's say that right here is the Sun. And then as you saw in the screencast, opposition is basically an alignment that looks like this. We have the Sun, and then we have right here the Earth, and then right here is the planet. As was noted in the screencast, this is referred to as opposition because as seen from the Earth, the planet is on the opposite side of the sky as opposed to the Sun. Okay, now the sidereal period of the planet. The sidereal period of the planet, very simply, is the amount of time it takes the planet to go from here to here. Notice that with respect to the background stars, in other words, think of the background stars as this classroom. The planet's position from here to here is the same. Once again, this is referred to as the planet's sidereal period. It's also known as its orbital period. It's basically the planet's true year. However, this is not what we see from our moving platform, because the next time that the planet is here in its orbit, the Earth is not here, because you have to remember that we're closer to the Sun than the planet is. We're moving at a different orbital speed. So then therefore, what can we easily see from our moving platform? We could see, for example, the time between this opposition that I've drawn here and the next opposition. The next opposition would look like this. So watch this. Like so. So let's say that right here now is the Earth. Let's say right here is the planet, and this is the next opposition. So we had the first opposition drawn earlier like so, and this is the second opposition like so. This is a rotation with respect to the Sun. In other words, as seen from the Sun, the position of the Earth and the planet is the same as it was earlier. We can see the next opposition because, once again, the planet very simply is on the opposite side of the sky as opposed to the Sun as seen from the Earth. So Copernicus realizes the difference between the two, that is the sidereal period and the synodic period, and he recognizes the significance of the synodic period. So if all that we could observe is the synodic period, how could you then use the synodic period to then calculate the planet's sidereal period? Well, basically what Copernicus does very simply is he counts laps around the Sun. How many trips around the Sun does each planet make? That is the Earth and this planet here on the diagram from, say, one opposition to the next. So let's take a look at those numbers. So for example, consider the Earth first of all. Notice that the Earth goes from here to here on this diagram in the time between one opposition to the next. So the Earth basically does this. So how many trips around the Sun does the Earth make? Well, it makes S trips around the Sun, the planet's synodic period. Think of it this way. Let's say at the time between here and here is 1 1/3 years, which is roughly what I've drawn here on this diagram. So then therefore, how many trips around the Sun does the Earth make? 1 1/3. In other words, the Earth makes S trips around the Sun, the synodic period. Okay, well, what about the planet? Well, the planet just goes from here to here, like so, on this diagram. Notice that the planet makes less than 1 trip around the Sun. How many trips around the Sun does the planet make? Well, it makes a fraction of its sidereal period, P, trips around the Sun. That fraction is S over P, and it's a number that is less than 1. So, for example, let's say at the time for the Earth to go from here to here is 1 1/3 years. This then means that the Earth made 1 1/3 trips around the sun, but the planet only made 1/3 of a trip around the sun. That's a number that is less than 1. That number that is less than 1 is a fraction of p. It's s over p. So the planet makes s over p trips around the sun. How can I get these numbers here and here to match up? In other words, how can I get this arrow associated with the planet to match up with this arrow here associated with the Earth? Well, if I just add 1 like so to the arrow associated with the planet, it will then match up with the arrow here associated with the Earth. In other words, take the s over p number, which is a number that is less than 1, add 1 to it, and you then get the same thing as s. So then therefore, s over p plus 1 is equal to s. It's important to realize that we aren't doing any physics here. All that we're doing is just looking at a diagram and then trying to get this arrow here associated with the Earth to match up with this arrow here associated with the planet. You do so by adding 1 to the arrow here associated with the planet. Algebraically, this expression here is rearranged a little bit. When you rearrange this expression algebraically, the expression is usually written like this. One over p equals 1 minus 1 over s. So here's the basic idea as to how you use this formula, say in the case of Mars. In the case of Mars, you measure the time to go from one opposition to the next. When you do, what you've measured here is the synodic period s. You then plug it into this formula, and this then allows you to calculate Mars's sidereal period, its orbital period in terms of years. So Copernicus applies this idea to Mars, Jupiter, and Saturn, and he arrives at values of p that are very close to their currently accepted values today. So he's starting to get the basic layout of the solar system correct. This counting scheme, if you will, for the inferior planets is done much the same way here as I did for the superior planets, but with one difference. You have to add the 1 to the other side of the expression. But here's what it looks like for inferior planets. Okay, now I'm going to use the same diagram here. I'm just going to change a few things on it like so, however, as I illustrate. And now specifically, this counting scheme here is going to be done for inferior planets. Take a moment and pause the lecture here, by the way, if you have to now just redraw this diagram here into your notes. But let me now also go ahead and add a few things. Okay, now the Earth is here, like so. And then let's say that the planet is here, either Mercury or Venus, like so. So from my screencast on the important planetary configurations, which specific configuration is this? It's inferior conjunction. Okay, now that's going to be the first time that inferior conjunction occurs on this diagram. And then the next time that inferior conjunction occurs, it looks like this, like so. So once again, here's the planet, here's the Earth, and now this is the next inferior conjunction. Okay, and then once again, very simply, all that we do here is we just count laps or trips around the sun. So first of all, take a look at the Earth. The Earth moves from here to here on this diagram. How many trips around the sun does the Earth make? Once again, that value is equal to s, the synodic period. So for example, let's say it takes 1/3 of a year, which is roughly what I have here on this diagram, to go from here to here. So then therefore, if the synodic period of the planet is 1/3 of a year, this then means that the Earth made 1/3 of a lap or trip around the sun. So once again, the Earth makes s trips around the sun. But then we have the planet. The planet moves from here to here on the diagram like so. Once again, the number of laps that the planet makes around the sun is the value of s over p, but in this case, it's a number that is greater than 1. So the planet makes s over p trips around the sun. Once again, how can you get the arrows here, the numbers to match up? Well, now what I have to do is I have to take the arrow associated with the Earth, add 1 to that like so, and that then gives me the arrow here associated with the planet. So I have to take S and add 1 to that, and that then gives me the same thing as S over P. Like so. So notice it's just a little bit backwards of what I did earlier for the superior planets. If you take this expression here and algebraically rearrange it a little bit, you end up with the following expression. This expression here. So here's then how you apply this expression. What you do is for Mercury or Venus, you measure the synodic period. You measure S, for example, the time from one inferior conjunction to the next. You then plug that value into here, and this then allows you to calculate P in terms of years. And that's, once again, the planet's orbital period, its sidereal period, getting here the basic layout of the solar system correct. So Copernicus then takes the data that he has for Mercury and Venus, plugs it into the expression to calculate the orbital periods of those two planets, and he arrives at values that are very close to their currently accepted values. That's basically the first part of Copernicus's math. I'll go through the second part in part 3 of this lecture.